almost all the processes that we discussed in the prior section are related to slope in some way. So it doesn't matter whether we have animals burrowing into the hillside and they're going to throw that dirt down the hill beneath them, because if they throw it uphill, it's going to be more work and it's going to refill their hole. Or if we're talking about overland flow, cruising across the surface, picking up sediment and moving it. And as this happens, that can produce rills, which are small channels that appear in the hillsides. Farmers are often well aware of rills, and often in farms that involve tillage, try to plow those out. But they are persistent and will reappear every year, especially if there aren't cover crops placed onto the soils. And these are zones where, these little channels where water can accumulate, and then that water can start to move soil downslope. Trees, through via their tree roots and frost, can lift soil perpendicularly to the hill slope, but then gravity pulls this material straight back down, which leads to a net downslope velocity vector. And that's, I'm just going to sketch this quickly over here, what we were talking about when I was showing you this kind of schematic hillside, and we have material being pushed up away from the hill slope, and then dropping down, straight down back onto the hillside, and then being pushed up away from it, and then dropping back down, and so forth. And through that pattern, there's overall a net downslope vector of Q sub m, which is mobile hill slope material. Rain splash is likewise able to transport less material uphill, and that's because this ejected material intersects the hill slope sooner and farther downhill, because it can fly farther before hitting the lower slope. And so you can think about this pretty easily, right? Like if you're just trying to throw a ball up a hill with all your strength, you're going to get a lot less far than if you're trying to throw it downhill, where that slope is actually helping you and lengthening the time before that ball crashes down onto the surface. So the idea here then, because I just drew rain splash up above in this last section in the prior lecture on a flat surface, so let's draw it on this rounded surface where I now have a rounded sloping surface where we now have this raindrop, this kind of streaky raindrop going down. And so, oh goodness, there we go, rain. And when that intersects the surface, that's going to cause some material to be ejected. And if I draw these arrows at approximately the same, angle and length, there we go, on both sides, what you can see is that this is going to have a trajectory that will ballistically hit down like that. And this one, it looks like it's, much steeper, but actually I drew it slightly less steep. And if I draw a similar ballistic trajectory coming from this, and this is just a cartoon, mind you, but, it's not so totally unrealistic, I actually have to extend, let's scroll down so I can get this onto this drawing pad. I have to extend this hill slope a little bit farther down this way. Pardon me. Alright, sorry about that with the phone. The prior time I was trying to record this, I got a knock at the door, but I'm just going to keep going so I don't have to keep on keeping on with this lecture. So this one going farther downhill is obviously going a lot farther for a similar ejection angle, and so likewise we're going to have a net downhill transport from rain. And the same thing as I've drawn above happens with tillage, right? So if we have, again, something like this, and we are inserting a plow into the soil, that plow is going to move less material uphill than it moves downhill, because if it's trying to create a mound that comes by after the plow passes, that's in gravitational equilibrium, right? It's not going to be able to have like a big super high thing on this side to match the amount of volume that's over here. Now, in order to have an even mound, it will have to end up moving more material down the hill slope than it is up the hill slope. So, plow. So what this means is that there's a lot of equifinality, and equifinality means that multiple processes create the same overall results. So what this means in this case is that it doesn't matter whether it's a worm lifting the soil, frost lifting the soil, a plow disturbing the soil, rain splash scattering the soil. a burrowing animal kicking stuff downhill, there are many, many, many natural and human-created processes that lead to material moving downhill. And if we think about this, on a flat surface, things like the plow would leave behind the same amount of soil on either side. On a flat surface, the gopher might just create a mound, which you might have actually seen, of soil above the hole. But whenever there's a hill, things will start to be kicked downhill, and if that hill is steeper, then if the gopher is kicking material out of its burrow, that's going to be able to roll and fall farther down the hill. So we can write this general rule of proportionality saying that the amount of material moved down the hill, so this is actually, in fact, this is volumetric discharge per unit width of material moved down the hill. I'm just going to point out to these letters because it's otherwise going to take me a while to write it all out. And this is in units of length squared per time, and so you can think that this is just so we can draw it on the page. It's kind of an area per time. If we're actually looking at a full volume, we're going to have to draw in 3 dimensions, and that's a little harder on a computer. Let's just wait for having the full-on holographic thing, and maybe we can eventually do this. And then over here, this S is slope. And so that is just the gradient in either a given direction or the steepest. And we can talk about slope in a given direction especially if we're thinking about this all in terms of our calculations on our page where we've already decided that we're looking down the steepest downslope direction, but the soil particles will generally move the most in the steepest direction downslope. So if we have this basic proportionality, we can then lump all of these different processes together into a single constant, and we're going to call this constant K sub HS. There's actually no convention in the literature for what we call this, but something that I'm going to try to do in the class is use K is constant, and then I'm going to have some sort of subscript of what is it. It, not if. What is it for? And so this is the constant of proportionality for the hill slopes. And so what I'm showing here now is that we have this Q sub m, so the rate at which this mobile material is moving is going to be equal to this constant of proportionality times dz dx. And so this is going to be the gradient in the x direction. And then I have this minus sign here. And the reason I have this minus sign is because dz dx, if a hill slope is going this way, and we have x over here and z over here, then dz over dx is greater than 0. And so if we were going with a positive sign, that would actually move hill slope material uphill. And so what we have to say is no, we want to move material downhill. So we put that minus sign there. And this case of HS term, so if we think about this, dz dx, so z is elevation, that has units of length, like meters. X also has units of meters. So this is unitless. But then this has units of length squared per time, meaning that this constant must also have units of length squared per time, which is the units that a diffusivity has. And so we talk about this term also as the hill slope diffusivity, even though it's not yet in a diffusion equation. And so this equation right here is totally analogous to something like Fourier's law of thermal conduction, if you've learned that before. And so what this is just saying is, sorry, still learning about how to use this writing pad, is that the rate of movement of material I want to say x is proportional to gradient. And in this case, the material movement is just the discharge of, per unit width of mobile material on the hill slope, and the gradient is the literal gradient of the hill slope itself. And so this case of HS is a super important black box term that lumps together a bunch of different processes. And so let's just think quickly. Scroll up here so we can get this box into the view as well as the equation about what things might affect it. So K sub HS goes up with, let's think, maybe it's going to go up with storminess, right? And this is going to lead to overland flow. Maybe it's going to go up with grazing. So there are more cattle walking across this, so ungulate hooves. Maybe it's going to increase with plowing / tillage, right? Or maybe it will increase as we have more freeze thaw. And perhaps it's going to go down with KHS down with more competent rock. Maybe it's going to go down as we have more vegetation cover. We noted that trees falling over can cause tree throw. Trees can also lift up soil with their roots, but then they also hold on to soil. So trees, it's a little unclear about what they do, but then vegetation cover in general reduces rain splash, reduces and reduces rilling, and so those might be important. Of course, these sorts of things are important for hill slope creep, not necessarily for landsliding. I've seen people try to revegetate hill slopes with shallowly rooting grasses in order to prevent landslides, and that really doesn't do a whole lot. But this can be important for the hill slope creep side. So just thinking about all the different terms that go into this and what kinds of knobs are actually being tuned into this final case of HS value. So with this, we have a relationship saying that the discharge per unit width of material moving down a hill slope is related to some constant of proportionality that might be related to the climate, the weather, the land use of a particular area, the animals. Forgot I'll even put in gophers. The biota in that area, and can also go down with other natural or human-induced processes such as vegetation. So there can be natural vegetation, we could plant vegetation. Prairie restoration in the northern plains could cause us to have these new deep-rooted prairie grasses reestablishing, or there could be more competent bedrock. So we're going to move from this next time into integrating this equation into a statement of mass balance to try to understand how hill slopes evolve overall and how to start to make some predictive relationships. And that's going to be another couple steps down the road. But here we are for starters, is that steeper slopes and slopes that have more factors that are causing material to move down slope faster will have more material move down slope faster. And then the last thing that I'm going to say, just to point out, is that this is a linear relationship. In other words, this discharge linearly increases as the slope increases, right? So there isn't a power, there's no natural log. Those two are just directly proportional to each other via this term called KHS.